Welcome to our presentation on multiple equation analysis, focusing on system estimation and vector autoregression modeling in EViews. As the EViews User Guide highlights, the structural approach uses economic theory to model the relationships among variables. This allows us to understand how different economic factors interact within a system rather than in isolation. We'll explore the methodologies and practical application using EViews. In the real world, economic variables are deeply interconnected and rarely move in isolation. For example, GDP influences interest rates, but interest rates also influence GDP. A major limitation of standard single equation OLS is its assumption that predictors are exogenous, meaning they are not influenced by the dependent variable. This is often violated in macroeconomics. The solution is system estimation, such as a VAR model, which treats all variables as endogenous, acknowledging their mutual influence. In macroeconomics, variables are often both independent and dependent. VARs, or vector autoregressions, sidestep identification problems by treating every endogenous variable as a function of the lagged values of all endogenous variables in the system. This decision matrix provides a clear roadmap for selecting the appropriate time series model when working with multiple time series data. The first critical question to address is whether your data is stationary. As the decision logic highlights, stationarity is essential for the stability of a standard vector autoregression, or VAR, model. If your data is indeed stationary, you can proceed with a standard VAR, unrestricted model. If your multiple time series data is found to be non-stationary, the next step involves checking for structural breaks. If structural breaks are present, a switching VAR model is often the most appropriate choice to account for different regimes or changes in the data's underlying process. However, if there are no structural breaks and the data is still non-stationary, you then need to test for co-integration. Co-integration means that your variables share a long-run trend. The decision logic explains that simply differencing co-integrated variables for a standard VAR would throw away valuable equilibrium information. Therefore, if co-integration exists, a VecECM, or vector error correction model, should be used instead to preserve this long-run relationship. Finally, if the non-stationary data is not co-integrated, the correct approach is to estimate a VAR in first differences, which effectively makes the series stationary before modeling. EViews provides a comprehensive toolkit for multiple equation analysis. For core estimation, it includes widely used models like the unrestricted VAR and the VECM. Most general analysis begins in the VAR object. For more complex structural systems, the system object offers methods such as SUR, 3SLS, and FIML. Beyond these, EViews features advanced extensions like the Bayesian VAR, useful for forecasting with many variables, the switching VAR for handling structural breaks, and mixed frequency VAR. Once a model is estimated, EViews offers powerful analysis tools, including impulse response and variance decomposition, as well as state space modeling using the Kalman filter. For unobserved components, analysts would utilize the S-space object. For example, an analyst studying the impact of the 2008 financial crisis on GDP growth and unemployment would use a switching VAR to allow the model's parameters to be different during the crisis regime compared to the normal regime. Let's dive into the software and see how to specify a basic VAR model in EViews. The reduced form VAR is the most common specification. Here, a vector of current variables, yt, is expressed as a function of its own past values and a vector of errors, et. This form is excellent for capturing short-run dynamics and for forecasting. The VECM is a restricted VAR for co-integrated series. It models the change in the variable, delta yt. It includes an error correction term, pi yt-1, which pushes the variables back towards their long-run equilibrium. The rank of the matrix pi, denoted as R, is critical. It tells us the number of co-integrating relationships. If R equals 0, there is no co-integration, and we use a VAR in differences. If the rank is full, the data is already stationary. If R is between 0 and the number of variables n, a VECM is required. First, we must check for stationarity and stability. For a VAR model to be stable, all inverse roots of the AR characteristic polynomial must lie within the unit circle. If any root is outside, the model is explosive, and its impulse responses are invalid. Second, the lag length is a crucial choice. We use information criteria like AIC, SIC, or HQ to select the optimal number of lags, balancing model fit against parsimony. Third, the model's residuals must behave like white noise. This means they should have no serial correlation, constant variance, homoscedasticity, and be normally distributed. Finally, the model parameters should be stable over the entire sample period. If there are structural breaks, a standard VAR may be inappropriate, and a switching VAR might be needed. After estimating a VAR, you plot the inverse AR roots and find one root is outside the unit circle. This is a critical warning. It means your system has an explosive response to shocks. The solution is to re-specify the model, perhaps by differencing the data or imposing co-integration constraints if they exist. Once we have a well-specified and stable model, we need to interpret the results. This is often done using two key tools. The impulse response function, or IRF, is a primary tool for interpretation. It traces the effect of a one-time shock in one variable on all other variables in the system over time, as shown in the left graph, where a shock to X has a decaying effect on Y. Variance decomposition provides complementary information. It tells us the proportion of the forecast error variance for each variable that can be attributed to shocks from itself and from the other variables, as seen in the right graph, showing variation in Y explained by X versus Z over time. A crucial point with standard VARs is the Cholesky ordering. The ordering of variables matters because it assumes that shocks to variables listed earlier have a contemporaneous effect on variables listed later, but not vice versa. This is a strong assumption, and understanding its implications is key to interpreting these results. To estimate a VAR model in EViews, you can navigate through the menu by selecting Quick from the main menu bar and then choosing Estimate VAR. This will open the VAR specification dialog where you can define your model. An alternative, and often quicker, method is to use the command line. As shown on the right, you can bypass the menu by typing a command directly into the EViews command window. For example, typing var myvar.ls12 gdp m1 rate will create a vector autoregression named myvar using the least squares estimation method, including lags from 1 to 2 and involving the variables gdp, m1, and rate. This command effectively sets up and estimates the VAR in one go, demonstrating an efficient way to interact with EViews. This slide illustrates the VAR specification dialog in EViews, which is where you define your vector autoregression model. In the endogenous variables field, you list the variables to be included in your system, like GDP, investment INV, and the consumer price index CPI, as shown in the example. These variables are treated as mutually dependent. The lag intervals field specifies the lags to be included for all endogenous variables. For instance, 1-4 means lags 1 through 4. Other basic options include whether to include constant or a trend in the model. On the right, under Advanced Options, you see instructions for Bayesian VARs. If you are using a Bayesian VAR, you would navigate to the Prior tab to set Litterman or Minnesota priors. These priors help to shrink coefficients toward 0, which effectively reduces noise and can improve forecasting accuracy, especially with many variables. This slide introduces the critical first step in setting up a VAR model, determining the optimal lag length. We use a table of VAR lag order selection criteria, often provided by statistical software like EViews. The table presents various information criteria, such as FPE, AIC, SC, and HQ, alongside the log likelihood and LR statistic for different lag orders. Our goal is to select the lag length where the majority of these criteria agree. For example, in the table provided, the asterisk indicates the minimum value for each criterion. We see that FPE, AIC, and SC all point to a lag length of 2. The pro tip on the right elaborates on these criteria. AIC, or Akake, tends to select more lags, which is often preferred for ensuring residuals are free of serial correlation. In contrast, SC, the Schwartz criterion, applies a heavier penalty for complexity and generally suggests fewer, more parsimonious lags. EViews consistently marks the winning lag length for each criterion with an asterisk. Therefore, following step 1, we would select a lag length of 2 for our VAR model, as indicated by the majority of the criteria. Step 2 is to ensure the estimated VAR model is stable. We do this by examining the inverse roots of the AR characteristic polynomial. For a stable model, all roots must lie inside the unit circle shown in the plot. This indicates that any shock to the system will eventually die out. If a root lies on the circle, it indicates a unit root. This suggests the variables may be non-stationary and co-integrated, and a VECM might be a better model. If any root is outside the circle, the model is unstable and explosive. The results, especially impulse responses, are invalid and should not be interpreted. You must respecify the model. The plot on the slide shows all the blue dots, which represent the inverse AR roots, are comfortably inside the unit circle. This confirms that our estimated VAR2 model is stable, and we can proceed with interpreting the results. Here we analyze the response of one variable to a shock in another. The scenario is a one-time shock to interest rates, represented by the T-bill. The solid blue line shows the point estimate of the response of GDP. We can see that GDP begins to decline after the shock, with the largest negative impact occurring after 2 to 4 quarters. The dotted red lines represent the confidence interval. For the result to be statistically significant, this interval should not cross the 0 line. In this case, the effect is significant from roughly quarter 2 to quarter 9. This analysis provides a dynamic story. An unexpected rise in interest rates has a delayed but significant negative impact on economic output. Looking at quarter 4, the chart shows that a 1 standard deviation shock to the T-bill rate leads to a roughly 0.8% deviation of GDP below its baseline trend. Since the confidence interval is entirely below 0 at this point, we can be confident this is not a random fluctuation. A structural VAR, or SVAR, moves beyond the statistical relationships of a standard VAR to identify causal structural shocks based on economic theory. The core idea is to impose restrictions on the contemporaneous relationships between variables, represented by the matrices A and B in the equation AET equals BUT. Unlike the Cholesky decomposition, which assumes a recursive ordering, SVAR allows the researcher to impose specific zeros based on economic theory. This allows for the identification of specific economic shocks, such as a monetary policy shock or a technology shock, and trace their effects through the economy. For example, as shown in the EViews dialog, one can impose restrictions like at A12 equals 0 and at A21 equals 0. The restriction at A12 equals 0 imposes that variable 2 has no contemporaneous effect on variable 1. A switching VAR, often a Markov switching model, is an advanced technique for analyzing time series that experience structural breaks or distinct regimes. This is extremely useful for modeling economic data that spans different environments, such as periods of normal growth versus periods of financial crisis or a pandemic. The model allows the parameters of the VAR, the coefficients, variances, and covariances, to be different across these unobserved states or regimes. EViews can estimate the model and also provide the probability of being in a particular regime, e.g. crisis, at each point in time, as illustrated by the shaded areas in the graph. The graph shows GDP growth. A switching VAR identifies 2 regimes: Regime 1, normal, with moderate fluctuations, and Regime 2, crisis, with high volatility, corresponding to events like the 2008 financial crisis. The model automatically detects these periods based on the data's behavior. State space models are a powerful framework for analyzing time series, especially when dealing with unobserved variables. They are defined by 2 core equations. The measurement equation, written as yt equals ht eta t plus et, connects the observed data, yt, to the underlying hidden state, eta t. The state equation, eta t equals ft eta t minus 1 plus ut, describes how this hidden state evolves over time. This approach is invaluable for modeling unobserved concepts like potential GDP or permanent income. When using EViews, the S-space object is the tool for implementing these models. It provides a text-based interface for specifying the system matrices and leverages the recursive Kalman filter algorithm for robust estimation of the hidden states. In EViews, once you have an estimated VAR or system of equations, you can create a model object to perform forecasting and scenario analysis. The model object combines all the estimated equations and any necessary identities into a single, solvable system. This